participants. Good morning to Brian in the US. Thank you all for attending this event. So today, SPE Java Indonesia, in collaboration with SPWLA Indonesia chapter, will be hosting our regular technical discussion group series. So the topic today is a discussion on fluid identification from NMR logs, which will be presented by our esteemed speaker, Brian Stambaugh. As the moderator, we have the pleasure of having my colleague, Mirza Media Adiosti. He is a senior geologist in Stambaugh, as well as the technical director for SPWLA Indonesia chapter. So in this session, I will accompany Mirza as the co-moderator. My name is Dian Permanasari. I am the senior Petrophysicist, currently working as the LWD domain champion with Stambaugh, Indonesia. So I am also representing SPE Java Indonesia section as the program chair for this year, especially the distinguished lecture and technical discussion group division. So before we dive into the main program, we have some promotion and announcements first to make. First, I will pass to SPE Java Indonesia section membership division chair, Pak Tommy Jamail. Pak Tommy, the time is yours.
Thank you, Bu Dian, and Brian, a warm welcome to you, and thanks for joining us for this session. My name is Tommy Jamail. I'm the member chairperson for the SPE Java Indonesia section for 2021 and 2022. And I just want to give a little bit of a brief reminder. I think it's important, obviously, with the membership and the support with everybody is what provides sessions like this that we're having right now. So, Budian, if you could go next, please. Thank you. Just to real quickly go over again the benefits of the SPE membership and so on. I'd like to outline a couple of things, and that's the benefits, obviously. And as I mentioned, sessions like we are in right now. But again, starting with the SPE online education, where webinars, obviously for members and so on, that are free with live presentations, on-demand training, training courses, and so on. And then you have the SPE Connect, which gives you the virtual, to communicate, exchange knowledge, and collaborate with other members from around the globe. SPE Live, that right there provides you with the latest news and technologies. I won't go over one by one for the sake of time, but a couple of my favorites, obviously, is a free subscription with JPT, the Journal of Petroleum Technology subscription that you would get via email. One Petro is also a very resourceful tool for technical papers and so on. Additional membership benefits that I have there listed on the right, obviously, it is free registration particularly for students. The one thing that we would like to definitely emphasize is for the student conversion to their young professional membership and so on. And that's something that we are definitely always, reminding. Volunteer opportunities that allows you to get some exposure and event time. And of course, becoming a mentor for us professionals and that. Get started as down at the bottom there, and you can register. The SPE obviously is now available in an application on your smartphone, which gives you information, which allows you to get involved. So next slide, please, Budian. Can you get the, okay, thank you. So it's pretty simple, obviously, with today's technology and that, but for either, new members who wish to register and join, you can go to spe.org/join, or for renewal of your membership. And then there's a list right there of, particularly for SPE Java section, for all of Indonesia, actually, the fees and so on. So my takeaway, is definitely, renew your memberships, join if you're not a member, and don't forget to convert your memberships and keep it maintained for fabulous events like we're here today, and a lot of other resources. So I think that's it. The next slide. Yeah, so that's it. If you have any questions of that, please leave them in the comment section. And definitely you're more than happy to contact myself directly, or again, you can go to the SPE website for additional details. So thank you very much.
Thank you, Pak Tommy, for the brief promotion. So next, our program division also wanted to make announcement. So SPE Java Indonesia section is currently opening opportunity for all SPE members, active SPE members, to participate as a speaker or moderator in our new technical program, which we call the SPE Member Virtual Talks. So we will host this event once or twice a month, which will also be open to all member and non-members alike. Yeah, so it's free registration. So this is very good opportunity for all SPE Java members to shine, share your interesting knowledge and experience, and gain more professional relations and visibility in the industry. Yeah, the requirement is very simple. You only need to be an active SPE. You have an active SPE membership. So do not miss this chance and register yourself in the link here. We will post the link in the chat box also later, so you can directly connect to the link. We'll open this registration until 30th of July. So don't forget to renew or register as SPE member. If you need any help from us, please do contact us. You can also follow us on social media to stay tuned and keep up to date with our events and activities. We will also post our recordings on SPE Java Indonesia section YouTube channels once available. Yeah. So lastly, I just want to explain a simple rule. During the presentation, please stay muted. Yeah, so that we don't disturb the session. You can type in your questions in the chat box later on, or you can also raise your hand and ask directly to Brian once allowed by the moderator. So only in the Q&A session. And then be patient and please wait your turn. Also, lastly, please be prepared to turn on your camera. We will take picture together for the documentation at the end of the session. For the participants, you can also download our virtual background in the chat box that we will provide later. So without wasting another moment, I will pass it on to Merza to introduce our esteemed speaker.
Okay, thank you, Badian. So can you hear me?
Yes, very good.
Okay, so good evening and good morning, ladies and gentlemen. Welcome to SPE SPWLA TDG Technical Discussion Forum Group today. We will have a special presenter today and we'll discuss about NMR logs for formation characterization and fluid identification. So let me introduce our speaker today. His name is Brian Stambaugh. He has 39 years of oil and gas industry experience with 24 years of that consulting on project worldwide. He was graduated from South Dakota School of Mines. He has a broad experience from Stambaugh to currently as a consultant at NMR Petrophysics LLC. He also has many experience on consulting projects to many oil and gas operators worldwide. And he also has many experience teaching 58 short courses related to magnetic resonance logging to 1,000 plus geoscientists and with unconventional resources since 1997. So I believe that we can get and ask a lot of things related to magnetic resonance to him. So during the session, we will have 45 to 60 minutes of Brian presenting his material. And after that, we will have Q&A session. So if you have any question, please write your name in the chat box with your question, or just please write your name so we can track down the order of the participant question. So without further ado, let's start the session. Brian, the time is yours.
Thank you.
Yeah.
Thank you for inviting me. One of my favorite assignments was in Indonesia, a month in Balikpapan in about 1995.
Oh, wow.
And
Long time ago.
yeah, I really enjoyed the time there. And then a little bit of time in Jakarta, and I think did a course for Halliburton 1998 in Jakarta. Please ask any questions, and I'll try to keep an eye on the chat box. But let's see. Trying to see. So, okay. Let me share my screen here. I'll try to keep an eye on the chat box for questions, but if I don't see it, somebody, okay, there, I've got it up also. So I should be able to see questions. So please, any questions at all, just I'll try to answer those. We did a session on permeability from NMR logs earlier a few weeks ago, and now we're going to talk about fluid characterization. And I want to review just how the tools work, and I apologize if you already sat through this in our prior session, but it's important to know how it works. Basically, the tool is a magnet, permanent magnet, and a radio transmitter. The permanent magnet polarizes the hydrogen, whether that's in the water, oil, gas, even in the minerals, actually. So the permanent magnet polarizes after the polarization time, which might be less than a second up to several seconds. The radio transmitter is turned on and the radio pulses are transmitted. That's step 2, and that's shown in the bottom here by let's see if I can turn on my laser. There we go. These red arrows are the radio pulses, RF pulses. And after the radio pulses, a spin echo is recorded. The scale is incorrect. Actually, up to several kilowatts of power are transmitted, but the spin echoes are very tiny. They are nanovolts. So the fundamental issue with the measurement is signal to noise. You're trying to see these nanovolt level signals, spin echoes, from noise. So a lot of work is done in that regard to try to improve signal to noise. So those are the steps: polarize hydrogen, transmit the RF pulses, and record these spin echo signals. Step 3 is to repeat the process, wait for the hydrogen to repolarize. Also, this sort of looks like a logging tool, but it's meant to represent a permanent magnet. In other words, north is not at the top of the logging tool magnet and south at the bottom. It's just a representation of a magnet. Okay, so this is a review of the experiment timing. This is important in order that you have an idea about T1 and T2. Basically, those are the kind of the key measurements we get from the spin echoes. We derive T1 and T2. So T1 is the time constant associated with this polarization. So as you're logging, the magnet or the logging tool comes up next to a part of the formation and the polarization begins. And that follows an exponential increase in the amount of polarization. The time constant for that polarization is T1. So the wait time shown here, TW or polarization time, it's sometimes called, might be less than a second. It might be up to several seconds, depending on what you're trying to do. So the polarization time or wait time is the overall time that you're polarizing before you start the pulses. T1 is that time constant of polarization. The reason that T1 is important, that time constant, you can see different things about the formation and the fluids. Shale formations will have a very short T1. They'll polarize. Hydrogen will polarize quickly. In a large pores, highly porous sand or carbonate, the T1 is longer and polarization takes place slowly. So that T1 can indicate kind of a formation texture or quality. Also fluid type. Oil, gas, water have different T1. And also for oil, different viscosity. Oil is different T1. So they're kind of two things intermixed, formation quality and fluid type within T1. So that's why it's important. So after the polarization time, in this display, I think these divisions are half millisecond or half second each. They're showing a polarization time of 1.5 seconds. So in this illustration, the polarization time or wait time is 1.5 seconds. So at that time, we start the radio transmitter, transmit these RF pulses. Again, they're several kilowatts in some cases. And then after each RF pulse, we listen for a spin echo. Again, they're nanovolt level signals, and might be just a few RF pulses and a few echoes, or it might be thousands, perhaps even 5,000 echoes. Again, depending on what you're trying to do with the what type of logging you're doing. Notice they decay. The spin echoes decay in time. And that's because the hydrogen has interaction with the pore walls, for one thing. In a shale formation, highly shale, there's a lot of interaction with the pore walls, and the hydrogen is influenced by the pore walls, and the decay happens quickly. If you're in a 30% porosity sandstone, there's much less interaction with the pore walls, so the decay happens slowly. The spin echoes will have amplitude far out in time in a high porosity in general. So that, again, T2 is just the time constant associated with that dephasing or the depolarization. So interaction with pore walls, rock quality, textures influences that decay, that T2. But also, again, just like T1, the fluid type, oil viscosity. So depending on the viscosity of the oil, there's highly viscous oil. There will be more interaction with the neighboring protons, and the dephasing will happen more quickly. Do you have viscous oil in Indonesia? By viscous, I mean more than maybe 10 centipoise, less than say 30 API. If so, that can influence both the T1 and T2. The third thing that affects the T2 or this decay is diffusion. So you're doing this experiment on the hydrogen, and while you're doing the experiment, the hydrogen in the oil, gas, or water is moving around in the pore space. That's diffusion. It's under the influence of the magnetic gradient field, so that the hydrogen is diffusing or moving around in the pore space. So the hydrogen doesn't rephase properly, doesn't come back into phase with these subsequent subsequent RF pulses. So diffusion also influences that T2. It doesn't influence the T1. The diffusion does not affect T1. It does affect T2. So T2, you've got interaction with pore walls first, fluid viscosity, fluid type, viscosity of the oil, and oil versus gas and water influence T2. Then thirdly, diffusion effects. Only on T2, not on T1 for diffusion. Does temperature affect T1 and T2? Yes, it does. There are some papers published about how the T2 is influenced. Sometimes it increases, sometimes it decreases. It sort of depends on the formation in the one study that came to mind. So that's the basics. T1 is the time constant associated with polarization affected by rock texture and fluid type, viscosity, and so on. And then T2 is the dephasing. In other words, all the hydrogen is polarized. We start the RF pulses, and how the hydrogen gets out of phase as you're trying to rephase it, refocus the hydrogen with the RF pulses, and it goes out of phase. The decay happens. So the whole experiment is repeated, polarize, RF pulses, dephase, and then repolarize over and over. So TE is the final thing we'll talk about. That's the time in between the echoes, inter-echo spacing, sometimes called TE. So that might be 0.2 milliseconds for some tools, and up to several milliseconds. If you're trying to do a diffusion experiment, we'll change that inter-echo spacing to get a better handle on diffusion. But that's the order of it, is generally like 0.2 milliseconds between the pulses, up to a few milliseconds. So any questions on that? T1, T2, any other questions? Just I'll keep an eye on the chat box. So the basic measurement is these spin echoes, and these are the spin echoes over on the right, these in the black. In this case, I think it was 1,000 echoes. I think that's right. And they're you can see that they're rather noisy. But that is our basic measurement. We're recording these spin echoes. And notice they don't have the nice character as in the illustration, there are actually some noise on there. And there's some different tricks you can do for noise reduction. You can do stacking, despiking, and different filters for the noise. So the echoes are a curve fit or inversion is done in order to see what the T2 is. What basically we're trying to solve for this exponential decay. So we look at these echoes and we try to do a curve fit to see what the T2 is. Is it very, very low T2, very quick decay? Or is it a very long decay? Or is it a combination? Usually it's a combination. Multi-exponential decay. So that curve fit is called an inversion. So the inversion or the curve fit is performed on these echoes, and we solve for the T2. We'll talk about T2 essentially. So in the green shaded is the T2. So in this case, this is a sand, kind of a clean sand, 25% porosity. Has a little bit of fast decay, low T2. That would indicate what? Well, that indicates generally clay or shale in a rock textural sense. And then most of the T2 is a very long decay. So it has a very long decay component. And that's what the curve fit or the inversion determined, was that at this depth down here, you can see my laser pointer, I think it's about 4,030 meters. The high porosity, it's a little bit of fast decay, maybe some clay, bound water, shale. And you can also see this on the decay, and then a very long decay. And let's go up to this shale, up to this depth, completely different character. There's a little bit of, or most of the decay is very quick. Like the initial decay happens, and there's nothing in the long decay. So that's typical of a shale. All the decay happens, and then there's not the long decay. This is just noise out there. And I had a question from Ari. I hope I'm saying it right. How does the tool know how long to wait until it fires the pulses? That's a great question. It is pre-programmed at the surface. You plan out what type of log would you like to acquire, a T1 or a T2 log, and the polarization time, and you sit down with the service company job planner, and they will plug in your porosity, temperature expected, and all that, and you come up with a plan, and that a forward model that indicates the likely polarization time that's needed for whatever formation you're looking at, and they will indicate, okay, we think we need a 10-second wait time, and we want to look for kind of a standard log, so we'll use a certain echo spacing, maybe 0.2 milliseconds. And those instructions are given to the logging engineer, and a preset, they call it an activation, which is basically a set of pulse trains that is pre-programmed, the echo spacing, the inner echo spacing, and the wait time and all that. And so the logging engineer does not have to worry about the fine details of it. It's kind of pre-planned, hopefully, according to the type of log you are recording. Thank you for that. So once you have this T2 distribution or T1 distribution, you can solve for porosity, and that's just the area under the curve. And then the bound fluid and free fluid is based on well, that's the unique thing about the tool, is it does not give you just porosity, but also also an idea of how much of that porosity is bound fluid and free fluid. No other tool could really do that before. Now, it doesn't measure the bound fluid as such. It's sort of indirect. You have to apply a cutoff. And 25 years ago, studies were done of formations all over the world to determine what that cutoff should be. And for clastics, it was determined to be 30 to 33 milliseconds. For carbonates, 90, 100, 110 milliseconds, more variable with carbonates. What is that cutoff? Well, it's just the dividing line on this distribution, and it doesn't show the logarithmic track here. I apologize for that, but it's the line dividing bound and free fluid. In other words, let's say it's a clastic and we just use 33 milliseconds. So in the software that you've used, put in 33 milliseconds. Any T2 below 33 milliseconds is assigned to bound fluid. Anything over past 33 milliseconds is free fluid. And you can recompute that later if you log it with 33 milliseconds. It's very easy to use just about any software, IP, TechLog, Geolog, Logic. You can recompute it with a different cutoff. And that line is not shown here, but if I could draw a line, it would be, that's, 33 milliseconds would be somewhere in there. It looks reasonable because it's kind of down the valley of where you'd expect. It seems to make sense with where the peaks are. In other words, free fluid is kind of intuitively off to the right and bound fluid is to the left. So it seems to make sense. And then another question was specific to this plot. You mentioned T2 distribution signal. Why is only T2 plotted? And well, this log was only recorded for T2. It's a pretty old data set, and they really couldn't do T1 at that time. So we didn't have T1. And then can T1 be used for the purpose as T2? Yes, it could. If we had a T2 or a T1 log, it would look about like this with the peaks, and we could divide it into bound and free fluid. We'll look at some examples of T1 logs too, and can use it largely the same way. But that's the basic idea. The spin echoes, you have the spin echoes, and then you do the inversion or the curve fit, and you get this T2 distribution. From the T2 distribution, you get porosity and then bound and free fluid. Okay, and then another question, why is T2 displayed commonly and more common than T1? Well, T2 was done for years, and it wasn't until 20 years ago or so when they invented LWD versions of these tools that they developed the T1 logging, and so it's just not as common. There aren't as many historically T1, not as many T1 logs, but T1 can be used very good. There just are not as many out there. And advantages to using T2 to get rock pore size distribution and fluid typing. Let's see, T2. Not particularly. There's probably more data out there for T2. There's more database. Another question, how to distinguish between clay-bound fluid and capillary water? We'll look at an example of that. It's kind of tricky. I mentioned that 33 milliseconds was a common cutoff, or 30 for bound and free fluid for plastics. 3 milliseconds is commonly accepted as the cutoff between clay-bound water and capillary-bound water. The clay-bound water has a lower T2. It's way down on the T2 spectrum. As a rule, not always, but 3 milliseconds is used as a clay-bound cutoff. But there's a lot of literature showing that may not be a great idea. A lot of studies show that it could be 3 milliseconds, it could be 40 milliseconds. So it's a little bit tricky to just use the clay versus capillary bound water. And what you'd need to do is take some core data and go to somewhere with a lab NMR device and determine the clay bound water content from that, and then see what it looks like on their lab NMR to really figure it out. And how about silty formations? Does the 33 milliseconds work in silty formations? 33 is just a guideline, and it can really be all over. It works pretty well for clastics, but it could vary a lot. There was a study done early on of the Travis Peak Formation in Texas, kind of a lower porosity shaly sand, and it showed that the T2 cutoff could be 10 milliseconds, it could be 70. So there's a big spread there. So, and you can determine that with again lab NMR data. So in deviated wells.
Hello, Brian. Sorry
Yes.
to interrupt you. So
That's
it's
okay.
really exciting that we have a very active participant, but let's do Q&A in the Q&A session. So we can finish the
keep going
presentation
here.
first. Yeah. Thank you.
Yep. You bet. Yeah, we need to get through all the slides too. So thank you for that and the questions. And this is just showing kind of a blown up illustration of the T2, the echo plot in a shale. This is a shale formation. Here's a gamma ray, rather high gamma ray shale formation, and rather low T2. It could be clay bound, capillary bound, or a combination of the two is likely. And then this is what the echo train looks like right at that depth. Very fast early decay, and then just noise. If you go down here, there's some. This might be the kind of a silty formation that was referred to in the question, and so there is some longer T2, maybe a larger pore size and a smaller one. There's actually 3 peaks, so maybe this is a case of capillary bound, or I mean clay bound on the very low T2, capillary bound, and free fluid. So that's where there's maybe you can distinguish the all of those. So if you were to say what is the cutoff between clay and capillary bound here, I would say it's right in here. Maybe draw a line in between there. It's about 1 to 2 milliseconds, not the 3 that we indicated as a standard. And if we use 33, that would be out here somewhere. That's more like 60 or so. It looks like 33 would not quite fit so well. So that's where you need to actually look at the individual the T2, and in most software you can actually draw a line and have a running T2 cutoff and compute it pretty easily. So where you have larger pores, see how there's a longer decay on the echo trains. An important thing we went over in the last talk was that this inversion or the solution of echo trains, the curve fit or the inversion to the T2 is not a unique solution. And there's different curve fitting methods. There's different ways of handling the noise. So that affects it. Yeah, this is a Shell paper from 2009. They ran a Halliburton Emerald and a Baker MR EX tool in the same well, and kind of a tight gas and 15% porosity, and T1 and T2, and the tools worked well. But the thing I want you to look at, there's the Baker result. Here's the yellow is the T2 plot. Here's the Halliburton result. Yellow is the T2 plot. Look at how different they are. The Baker result is rather smooth, and the Halliburton result is not smooth, much more active. And it's not really the tool difference in the tools. Echoes are echoes. You know, really, the tool, probably the raw echo data is somewhat similar from the tools, so it's all in the smoothing. So that's very important to think about, that they both, neither inversion is right or wrong. They're just different. One is more smooth than the other. And if you look right down here, there's some late T2 that appears with the Halliburton processing, and not much evident with Baker. So conceivably, you could miss something about pore types or so on if you do too much smoothing. But that's just important to bear in mind, that the inversions are different. That's a good paper. Oh, both tools gave about the same porosity, similar volumetrics, and so on. Oh, okay, so the logging tools in the late 1990s, these were the two designs. Was the CMR, that was a pad type tool, X-centered against the borehole wall, and the Emerald, that was the Halliburton tool. And the CMR basically was up against the borehole wall, and this is a top-down view of it with the magnet, the antenna. The sensed volume was out about, say, an inch roughly into the formation. And it has to operate at one frequency, because that is where the field is focused. That's where the permanent magnetic field is optimized at that certain depth. You've got to be on that frequency and just use that frequency. Then they came out with the CMR Plus that had some improvements. The other design was the Emerald tool, and basically it was a centralized design and had a gradient field. And the nice thing about that was that you could see different depths of investigation. So you could see different bands, and that's what this is meant to show in this top-down view. So all you have to do is change frequencies. You'd be looking at a different depth of investigation. That's the advantage of that design. One of the disadvantages was if you'd have to transmit, since it was centralized, you had to transmit the RF energy across the borehole fluid, and the spin echoes are just nanovolts. They had to come back to the antenna. So if you were in saline mud, the RF energy, the energy was dissipated by the saline mud. You can't really change frequencies with this type of tool design. If you change frequencies, you'll be off resonance and out of that sensed volume, or out of the optimum magnetic field. So now the tools now are, they've all kind of converged on a similar design. That is kind of a large pad type design. These include the Baker Hughes MRE Explorer, it's a large X-centered tool with a bowspring, and it sees out to the side of the tool, and the gradient is designed such that you can change frequencies and see different depths. The Halliburton they still have the Emerald, but they've got the Emerald XL that's X-centered, and now the XMR that's X-centered and multiple frequencies, multiple depths of investigation. Schlumberger still has the CMR. I think it's called a Magnify at this point, but also the MRX scanner. Same idea, large antenna that X-centered, sees out several depths of investigation out into the formation. Also has a high resolution antenna that sees shallower, so that's kind of a nice feature. And Weatherford has the FMR that recently came out with a couple of years ago. Similar design. So all the major service companies have converged on this type of design. That larger antenna, X-centered, don't have to transmit across the borehole fluid, and you can see several depths of investigation. So they're all great tools. The only one that you really can't change frequency is well, yeah. Let's see. Well, yeah, you can with that, but those are all these are basically the same design. So, oops. Oh, the logging tools have advanced so much in 30 years. This was the first commercial Emerald log. It only got 50 echoes and recorded at 90 feet per hour. The tools up now, such as the Halliburton Examiner, over 24,000 echoes, 6 different wait times, 18 different echo spacings at a few hundred feet per hour. Just a phenomenal evolution in the technology. And the nice thing about that is you can do several types of measurements at once, T1, T2 diffusion. So anyway, that's kind of an overview of the technology. So for fluid characterization, the great thing about it is it's independent of resistivity analysis. So you don't need to worry about Archie equation, M and N, RW, none of that. In fact, one of the early places this technology, fluid ID, was used was in Duri Field and in Indonesia, where Archie analysis, I think, could be problematic, and you could see the oil signal more directly with these tools. That's in the mid-90s. So the downside of it is that the tools only see 1 to 4 inches in depth, and so it's kind of SXO or shallow depth of investigation. Oh, the other thing is, I think someone mentioned in a question about oil-based mud filter rate. The conventional thinking was oil-based mud does not invade, but the oil-based mud filter rate almost always invades. You can always see it with the tool, and that can present an issue that if you're looking for oil in a well drilled with, if you're looking for oil with fluid NMR, well drilled with oil-based mud, you're going to see oil in the form of oil-based mud filtrate. May not be the type you're looking for, but you do always see it. So really the 6 ways of doing this fluid characterization is just look at the T2. We'll look at some examples of that. Very simple. The other thing is change the wait time and do what's called a differential spectrum. Change the echo spacings. So remember that plot where we were looking at the pulse timing, T1, T2, and the wait time and the inner echo spacing. Well, all we can do is change those parameters. We can change the wait time, we can change the echo spacing and look at diffusion. Another one that's sort of independent of those ideas is to compare the NMR porosity and density porosity. fifth one is to look at the T1. Just record a T1 log, and oftentimes hydrocarbon signal will show up directly on the T1 log. Then a sixth one that evolved was that many of the newer tools can see different depths, 1, 2, 3, 4 inches. And interestingly, the fluid type is different oftentimes at those different depths. So whether you're doing T1, T2, or diffusion, you might see a different result. So for example, at 1 inch depth, you might see more water-based or water from the water-based mud or oil from the oil-based mud. But deeper, you can see, even though it's only 2, 3, 4 inches, you might see a change in the fluid type to more of a native fluid. So that was kind of interesting. So these can be just this T1, T2 diffusion can be just displayed on the log, or they're often displayed as cross plots. So those are really the 6 ways we can do this. So the first one we'll look at is just look at the T2. You may have a large database, a relatively large database of just older T2 logs. That's most of the logs recorded in the past history, 10, 20, 30 years are T2 logs. In this case, in West Texas, they found that if you had any T2 beyond 210 milliseconds, they drew a line there, that red line, it's probably oil. This was a West Texas carbonate, and they just figured that out from enough wells they had and mud logs, and they figured out that this works. This doesn't work everywhere, but in this case it does. It did work. So that's just look at the T2 and might be applicable. Here's another case. Let's see here. These are there's a gamma ray caliper in the first track, resistivity, and the NMR permeability. Notice on the resistivity, very low, and then all of a sudden looks like you might have a oil water contact or some type of contact right here, right? Goes to higher resistivity. And here's the T2 plot. For some reason it's not shaded, but you get the idea. Look at what happens at that contact. The T2 shifts to the left. Right, it just so happens that it's right at that contact. So in this case, the T2 is it's probably a more viscous oil, but this is a case where the T2 is more influenced. It happens to be a more viscous oil, and it shifted the T2 downward. So this is another case where you could just look at the T2, and from other data, they knew that it wasn't a change in the rock type, that it was actually a change in the from water to viscous oil. One more example. In this case, this is an oil-water contact. So here's resistivity. The deep resistivity increases right here. Porosity is relatively constant at about, 15 to 20%. And I should discuss this a little more. The gray is capillary bound fluid. This is how Halliburton displays, or did display, a lot of the process logs. The gray is capillary bound water. The green is clay bound water, so probably everything below 3 milliseconds. The red is free hydrocarbon, and the blue is free water. So that's that type of display. The yellow they're calling gas for some reason. But the interesting thing about this example, look what happens when you go from low resistivity to high, that's probably an oil water contact. Look what happens on the T2. Now this T2 plot, the way that Halliburton displayed it was sometimes they'd have a separate track here, 0.5 to 4 milliseconds. So that's, I guess they were using 4 as a clay-bound cutoff. That's just how they displayed the log. So this is the very early T2 they're assuming to be clay. Schlumberger calls it just small pore porosity. I think that's probably a more accurate term. You don't know for sure that it's clay bound. And then the remainder of the T2 from 4 to 1024 milliseconds is displayed here. Very interesting thing happens right here in the water. You see a little bit of a very early peak that might be clay bound, and then a later peak, free fluid. Look what happens in the oil contact. It splits into three modes or 3 peaks. Or you very often see this when you go from water into oil. You get a splitting out of these peaks. So all of a sudden you get this early peak, it's clay bound, middle one capillary, and the late one due to oil. So look for that on the T2. Very often that happens. Okay, so that's the easiest, the most simple one that might work. You might be able to just look at the T2 log and see the fluid type change. Not guaranteed, but it is simple. And the next one is called differential spectrum. And basically, I need to go back here to this plot, and I need to ask you a question. In this case, it looks like we were fully polarized by 1 or 1.5 seconds, right? Okay, who can tell me what if we didn't use 1 second or 1.5 seconds? What's going to happen if we use a half second for wait time or polarization time? If anybody wants to put the answer in the chat, that's fine, but we're not going to be fully polarized. So when we start the experiment, our porosity will be low. In this case, if we just used a half second wait time, our porosity would be low by that much. It looks like it'd be about 20% low. If we only used like 2/10 of a second wait time, our porosity would be about half. So that's the basis of doing differential spectrum, is that the basic experiment, you want to use it long enough polarization time to get all porosity. That's doing the log correctly, right? Differential spectrum, you do that, but then you do another measurement with a very short wait time. And what happens is you miss the hydrocarbon signal. So that the standard long wait time, you get all the water signal. Let's say you're in the hydrocarbon column. The only water signal is probably in the bound fluid. So you get all that signal. Here's the gas signal. Get all that signal that you're going to get. And then the light oil, let's say it's a light oil. Say we have light oil, gas, and water, bound water in this case. You use a long enough wait time, you'll recover all or most of all of those. By a long wait time, I mean 8, 10 seconds, 13 seconds. Okay, what if we do another measurement with a short wait time, like 1 second? Well, we might, 1 second, you might still get all the bound water, but the gas signal, light oil, will be greatly diminished because they have a longer T1. They take a long time to polarize light oil and gas. You're going to miss that signal. So it's kind of like you do the experiment right, you do the experiment wrong. But if you subtract those signals, you essentially end up with two different T2 spectrums. If you take the difference, the bound water drops out and you're left with a gas and oil signal. So that's directly identifying the gas that has a shorter T2 and the light oil. So you long wait time, short wait time, take the difference, and there you go. And I had to think about this for a long time for it to make sense. So don't feel bad if it's confusing, but that's just something you have to think about. So again, that experiment timing, using short of a wait time, you miss some of the porosity on the gas and light oil. Here's an example of that. This is a case where you really can see the answer from standard logs. Here's a sand, shaly sand on the gamma ray, resistivity, high resistivity indicating hydrocarbon. And then here's neutron and density. Here's at the top, you have a lot of crossover, so it's probably gas. In the bottom, you don't have a lot of crossover, it's probably oil. So it looks like gas on top of oil just based on the triple combo logs, right? Okay, so here's the differential spectrum with NMR. Here's the long wait time. In this one, instead of a waveform, it's shown as color amplitude. The purple is kind of a higher amplitude. And here's the short wait time. And here's the difference signal. So you get a long T2 in the oil, so it's probably a light oil. Up in the gas, you see a little bit of signal there. That's a short T2. That's your gas signal. That's basically how it works. You have the long wait time minus the short wait time spectrum, and see what signal drops out. And short T2 is gas, long T2 is light oil. So that's differential spectrum. Here's another example. This is a kind of a tight gas sand in East Texas or Louisiana. And oftentimes Halliburton would display this difference, the standard T2 on a blue background and the differential on a gray background in going back historically. And the difference signal shows, well, they don't have the scale here, but it's T2 of 170 milliseconds. So gas with the Emerald tool was generally under 100 milliseconds. This isn't quite down to gas, so they're thinking it's a rich gas, and sure enough, it produced gas plus oil. Here it has T2, 1500 milliseconds, indicating light oil, and sure enough, it's how the differential spectrum was used. The standard T2, you don't see that hydrocarbon type. Really, it just shows good pore space here. Same here. It doesn't really distinguish it on the standard T2. It takes the differential spectrum to see the gas versus oil. Okay, so the next that's basically changing the wait time. The next one that was developed was just comparing NMR porosity to density porosity. In this example, CMR example, and the neutron density does not show any gas crossover. So it doesn't look like a gas zone, but if you plot the NMR porosity called the TCMR, along with it, it shows much lower than the density. Okay, so that is indicating gas. So I thought to myself, why don't we see that on the neutron density? Isn't it just like looking at neutron density crossover? Well, not exactly, because a neutron sees all the hydrogen in the formation gas. It actually picks up the hydrogen in the clay hydroxyls. The NMR does not. The NMR cannot see that, and so it has an advantage over the neutron. So in other words, the neutron sees the hydrogen that's in the actually chemically making up the clay, and that's not bound. It's not clay bound. It's not capillary bound. It's actually part of the clay hydroxyls. That's NMR doesn't see that. So that's the difference. But it works pretty well. You can Schlumberger invented this technique, and it works with any tool. Look for the NMR porosity to read lower than the density porosity. Could be gas. Of course, the density porosity has to be on the right matrix. If you're in a sand, it's got to be on a sand matrix. Lime, it's got to be on the lime matrix. So that's a slight complication, but it works very well. Another example, we'll just a little bit crunched for time, so we'll just pass over that one, but it's the same idea. Okay. The other idea that one of the 6 methods of fluid identification was to look at these techniques versus depth of investigation with the Schlumberger's and MRX scanner tool. You can see 1.5 inches depth of investigation, 2.7 inches and 4 inches depth. And so the porosities are shown here. The black is 1.5 inches. The blue porosity is 2.7 inches. And you can see a porosity reduction. The deeper, just a little bit deeper, the porosity is reduced. So you're thinking that gas has not flushed as much, even that much deeper, from 1.5 to 2.7 inches. So that's the beginning idea of how you can use different depths to see how the saturation is changing. Even the porosity would change. Let's see. So the next idea is T1 logging. And the beauty of that idea is that gas has a very long T1. So if you in this case the T1 plot is shown with the red shading for this Halliburton log. The standard T2 plot is on blue shading, blue background, and in this case, this is kind of a tight gas sand. It's about 9% porosity. And as the T1 of gas in this case is around several thousand milliseconds. Well, sure enough, there's a signal out there, way out and farther than would be expected for normal water in pore space. So you can look directly at the T1 and see that that's likely a gas zone. Let's see, this bottom zone, not so much gas signal. So all the T1 is lower, it's probably water. This zone, probably gas. So you can look at the T1 directly. And the way that we get T1 actually is, again, to intentionally do the experiment wrong. For a standard log, we use a long polarization time. For a T1 log, We do the experiment incorrectly several times. In other words, we'll use a very short wait time, maybe 0.2 of a millisecond, 0.2 of a second, I mean, half second, 1 second, 1.5. If we do that, just with a few brief experiments, different polarization times, we can figure out, we can solve for the T1. So you're doing several experiments at different polarization times to get the T1. The advantage of T1 is that you can do those experiments fairly quickly with just a few echoes, potentially logging faster. With a T2 log, it might be hundreds or thousands of echoes. With the T1 log, it's just a few echoes at each wait time. Not nearly as much power is used by the tool. So just a few echoes at several wait times, you figure out that polarization, that profile of the polarization in that method, in that manner. So that's T1 logging. Another thing we can do, we looked at changing the wait time and then taking the difference signal. What if we change, sorry, jumping around a little bit. So we change the wait time for differential spectrum. What happens if we change the echo spacing? Well, that's the other thing we can do with NMR tool, is change the echo spacing. What happens in the standard experiment with a short echo spacing, water will have a certain T2, gas has a certain T2, oil has a certain T2 depending on the viscosity. The interesting thing is if we use a much longer echo spacing, say if we go from less than a millisecond to 6 milliseconds echo spacing, the water shifts a little bit. Gas really shifts. The reason that happens, we use a long echo spacing. We're doing this NMR experiment with these spin echoes, with the RF pulses. If we wait a long time between pulses, that gas has a long time to move in the pore space. That's diffusion. Okay. If we use a short echo spacing, it's still moving in the pore space, not nearly as much. We use a long echo spacing. Gas is very mobile. We see a big shift. Oil, not so much. Water, somewhat, but it's really, really good for seeing gas. This is from an old CMR job planning spreadsheet. And it just shows, you input the temperature, pressure, estimated viscosity of your oil. It just shows where the diffusion, amount of diffusion on the y-axis, temperatures on the x-axis, but the amount of diffusion for the gas, water, and oil. Look at gas. It's an order of magnitude higher than water. That just makes sense. Gas is mobile. You're trying to do this experiment and the gas molecules are diffusing. Water has some diffusion, not nearly as much. Oil is less, about an order of magnitude lower. So if you get to viscous oil, it quickly goes to 1, 2, 3 orders of magnitude at 500 centipoise oil. So you can see how there's several orders of magnitude difference in diffusion between gas, water, and oil. So if we change that echo spacing, that's what makes diffusion happen. And this is an example of Halliburton example of a diffusion log. And we can see the water hydrocarbon contact here, but the resistivity greatly increases. It's pretty easy to see. And we see a shift from the water. This is a T2 of the water line as maybe determined from a job planner. We know based on temperature and so on about where water should be. And then a shift to the right shows something other than water. So the idea evolved about 20 years ago was, what if we changed echo spacing to get diffusion? And Schlumberger came up with this idea of magnetic resonance fluid characterization in the lab from say 0.2 to 2 to 4 milliseconds, several different echo spacings that we can do with the tool. We could see in the lab, see the water shift and how much it shifted. In other words, how much the T2 shifts with when we change the echo spacing. So this was cataloged. The same experiment was done with 100 centipoise oil. Not much shift, regardless of the echo spacing. There's just not much diffusion with viscous oil. 10 centipoise oil, more of a T2 shift. So all this was cataloged. Light oil, 1 centipoise, quite a bit of a T2 shift. So all this was characterized, all the different fluids and viscosities at different echo spacings for that tool. So you can envision, if you had this knowledge or this database, that if you ran a log with different echo spacings, you could actually solve for viscosity and oil and fluid type. And that's exactly what they did with the MRF method. Multiple echo spacings, and with the scanner tool, it was a moving log. With the CMR, it was a station log, but you could actually plot viscosity and oil volume. Okay, so this is a case where the results are shown on a log, but the idea came about to show these on a cross plot. So this is a diffusion measurement at different depths of investigation. So so on these cross plots, gas, these are T2 versus diffusion plots. Water is along this blue line, oil is on the slanted line depending on viscosity, and gas is up above. So from this log example, in the upper sand, they see at the shallow depth, probably 1.5 inches, a little bit of gas signal, and then another signal that's not on any line. So they're deciding it must be gas cut oil-based mud. It's drilled with oil-based mud, but you're not seeing all oil-based mud filtrate signal. It's upward somewhat. So they decided it was gas cut oil-based mud. But at the deeper depth, that's probably 2.7 inches. Look, the gas signal increases. So this is an example of using the different depths and looking at how the saturation changes and trying to infer the fluid type. So you get a little bit more gas signal, just a little bit deeper in the formation. Same thing here. This is let's see, this is a gas contact. So yeah, at 1.5 inches, no gas signal, nothing on that line. 4 inches, look, gas signal appears. How about in the oil column? Okay, at 1.5 inches, oh, this was drilled with oil-based mud. Sure enough, we see an oil signal. And then deeper, we see kind of a stronger oil signal. It's kind of hard to say whether it's the native oil or oil-based mud. It's kind of tricky. Down in the water column, you still see an oil-based mud signal in either case. So oil-based mud can complicate the situation a little bit, but you do see you do see gas increase at deeper depths. So that's all the idea of looking at all these measurements at different depths. Another example, and I'll kind of close out here. 1.5, 2.7, 4 inches. Again, looking at, this is T1 versus diffusion, but it could be T2 versus diffusion. Similar idea that at the deeper depth, you see a stronger signal. Here in the water column, it's basically, interestingly, it's on the water line regardless of the depth. So that's the idea of using, in that case, T1 logging, different depths. So we looked at those 6 ways. Probably have more standard T2 logs in whatever area you're looking at than anything. So sometimes you can just look at the T2 and see a hydrocarbon signal, see the signal split out into a bimodal. The other thing, we can change the wait time, look at a differential spectrum. Change the echo spacing, make diffusion happen. So if we use a long echo spacing, there's time for that diffusion to happen and look at diffusion. Something really different is just to look at the difference in NMR porosity and density porosity. The 5th one is just to look at the T1 log. And then the last one is to look at these any of those methods at different depths. With the newer tools, see different depths of investigation. And that slide talks a bit about job planning, but I'll wrap it up, and please, any questions I can answer. It's a lot of information, and we could probably spend a whole day or half day looking at all that. So thank you. Okay, the one question was, in case of deviated wells, the tool's not centralized, not reading the formation properly. How do we recognize it? Well, that can be tricky. If the porosity is higher than expected, that's a key one. Typically bound, if you see a borehole signal, it is seen as higher bound fluid and higher porosity than the other logs. That's the typical case. And how does the oil-based mud signal look like? Well, it looks like light oil. So it will have the same T2 and T1 that the light oil will have. And you can, one way you might be able to help separate those is work with the service company job planner, and they can put in their spreadsheet, their job planning spreadsheet, what your expected oil viscosity and temperature is in the area you are working, and they can tell you about what the T2 will be, and the T1. In other words, they'll have a job planner, something like this one. This is an old one, but you input the temperature, reservoir pressure, and the viscosity. Well, you can see what the T1 and T2 will be for the different different oil viscosity, and compare that to the oil-based mud, T1 and T2. Okay. Oh, the difference between KTM and KSDR that were shown, that permeabilities on the plot, that TM is the Timur-Coates equation, and the SDR is another equation that's the SDR equation. It's a little bit different equation in the permeability. They're usually somewhat similar. Okay, do you think the fluid types by NMR works if it's fractured carbonate? Oh, that's really tricky. At low porosity, average porosity around 4 pu, that's hard. It might work. The problem is that the tools are counting hydrogen, and at 4 pu, you just don't have a lot of hydrogen. One way you can do it is to take station logs or log extremely slow. I don't know how big the area zone of interest is, but if the whole thing is signal to noise. So with low porosity, you don't have a lot of signal. So you want to stack the signal. And there are ways, I use a program called Logic software out of the UK for NMR work. And you can actually download a demo and play with it. They'll let you try it. But you can, if let's say you have a 30-meter thick formation, you can stack all the echo data for the entire 30 meters, and it will have better odds of seeing a hydrocarbon signal. The more data, more echoes you can stack because of the low signal to noise.
Hi, Brian, sorry to interrupt you. So, hello?
Yes, no problem.
Okay. So I have one question that you answered before, but it's not very clear until now from Pak Yulianto Jong. If I'm not misunderstanding, the T1 and T2 distribution will give us the rock petrophysics properties and the fluid types or viscosity. But why most of the time the T2 distribution is displayed in the common NMR log layout than the T1 distribution? Is there any advantage to use the T2 distribution to derive the rock pore size distribution and the fluid tapping? I mean, why we don't see much the T1?
Yeah, the T1 logs are not as common. They're not. It's more relatively newer, and so they're not as common. There's more data, rock data with T2 from lab NMR that tying that to the rock data. So I guess in general, it's better just because of the majority of data. But on the other hand, T1 does not have any diffusion effects, so that takes out one of the variables. You're just looking at the hydrocarbon or the fluid effect on T1 and the rock texture effect. So it does have that advantage.
See, so
oh, go ahead. Sorry.
Okay. So Pak Yulianto, do you have any comment on that, or do you satisfied with the answer? All right. I think it's already cool.
Okay.
Okay, so we can continue with the next.
Okay.
Yes, okay.
The other part of this question, with the question about the 4 pu carbonate, this is saturated oil reservoir, 20 API, a high paraffin, 55 DC pour point, gas cap is 85% CO2. So with the high CO2, you won't see that gas because it doesn't have any hydrogen in it. Okay, so for 20 API, that's very viscous. That's going to have a very low T2 and low T1. So that might help, because what's going to happen is a normal carbonate generally has a longer T2, not always, but generally a carbonate with saturated with water has a longer T1 and T2. You could verify that in your case with lab NMR data. You also mentioned that it's fractured. Wow, so there's no matrix porosity. So yeah, you know, with viscous oil, I think you'd see that oil maybe either on a T1 or T2 as a shift to the left on T1 or T2. So if you had, let's say you had fractured carbonate porosity 4 PU in a water zone, I think the T1 and T2 would be longer. If you got into a 20 API oil zone, it's going to shift to the left, I think. So there's a good chance maybe it would see it even though the porosity is low. It'd be an interesting application. Okay, the 3 PU porosity level for the reliable gas detection. That's what they came up with in that Shell paper from 2009. They said if you got below about 3 PU, it's hard to see the gas on T1 or T2. That's the I think they're referring. I guess I'd have to look back at that paper. I think they were referring to the free fluid part. So below that level, there's just not enough hydrogen to count. So it's tricky. Again, you could stack the data, you could do a station, you could log extremely slow to improve your chances. Under polarization, yeah. Oh, okay. Yeah, you don't see very light hydrocarbon. Movable oil and unmovable oils. Okay, and the fluid characterization of NMR differentiate between movable oil and unmovable oil. Well, yeah, there have been some interesting studies done with residual oil saturation. They would, let's see, they would run a NMR log and then underream the well, the borehole, and dope the drilling fluid with what was it, magnesium something, a chemical or compound that would kill the NMR signal. So they'd underream it with the Mn magnesium chloride, maybe, or sodium magnum. Anyway, we can look it up in a paper, but that was in the mud. So when you underreamed it, that would invade, or that would be in the pore space, and then log it again. And that magnesium stuff would kill the NMR signal. So wherever they still had NMR signal, was not movable. Yeah, it was not movable because it was still, the signal was still there. So that's been used to determine movable and unmovable oil. There's, yeah, that's one that comes to mind. Thank you for that. Okay, if I have gross reservoir 10 meters, but it's shaly sand with 2 meter thick of each sand, how do we acquire to distinguish sand and shale properties? That's a good question. So it's a 10 meter reservoir, 2 meter thick sand. So let's see if you, okay, so let's think about most of the modern tools have about an 18-inch, what's that, about half a meter antenna height by the, and the data is stacked. There's with a running average. So by the time you stack the data, it gets sort of smeared, and 2 meters, that's like, yeah, it will pick up a 2-meter zone, but it doesn't fully resolve. You have some shoulder effects. It will fully resolve that bed, but one that might be a case where you want to run the CMR because it has a shorter antenna, fundamentally has better bed resolution over the newer tools. The newer tools have a longer antenna, which the bed resolution is longer and more smoothed in that case, but it gets better. You can do more with that data. Whereas the CMR has a shorter antenna. The other thing is the scanner has that high-res antenna that could help there. And the other thing you can do is log very slow and with a minimal running average. In other words, those echo trains are stacked as you're logging in order to get good repeatability. So if you're logging very slow, that will enhance your bed resolution in that case. Okay, recommendation for lab procedure, how to obtain T1 or T2 cutoff of reservoir condition. On lab data, they can typically take your core sample and do those tests at reservoir conditions. So that's one way. The other way is to just look at the log, and sometimes, let's see, go back to this example. Well, that's not a good display. Let me go back to a good example. This is an example of that. So what I like to do is just look at the data and see where the valleys are. In other words, a likely free fluid versus bound fluid is right here. And most software, you can, like IP and power log and so on, you can draw a line down that valley to determine, draw your own cutoff. So you don't need any lab data. You just look at your T2 and draw in the valley where you think the bound versus free fluid is. Let's look at this one. So you just draw the line there, maybe there. It's kind of a judgment, and then that'd be your clay cutoff. Here would be the capillary bound cutoff, and it's not always clear. It's not always separate peaks, but that's worth a try. This is a great example. Like right here, you could just interactively draw the capillary bound and clay bound right there and right there, so that your boss would be very happy because you're not spending any money on core data, and you're getting it at reservoir conditions because that's what the logging tool saw, and it's probably more correct. There's a lot of tricks to doing lab data too that we don't have time to go into all that, but basically it's a little bit tricky sometimes to get the lab data to make sense with the logging tool data. Okay, so let's.
Thank you, Brian.
Yes.
Let me just read the question from Chris Platt. Yeah.
Okay.
So does salinity variation or formation water chemistry variation have an effect on T1, T2, or diffusion properties?
It can. There are. I'm trying to think of anything I've read about the chemistry. I know some of the there's a paper written on brine formate, I think it was, affecting the T1 and T2. That was a drilling mud additive. I think it was called formate brine solutions that greatly affected the T1, T2. I can't, let's see, I'm not remembering anything else on the water chemistry affecting it. The salinity variation has a slight effect on the porosity. I can't recall anything about the T1, T2 diffusion, other than that formate brine mud additive. And then the other part of that.
And then the next question from Chris Platt. He mentioned that we really need to do NMR planning with different fluid types to understand the T1 and T2 versus diffusion map signals. Then, so he's commenting that it is very important to do an NMR planning in this case, yeah, to identify the fluid type.
Exactly. Yeah, those forward modeling spreadsheets, or not spreadsheet. Some of them are spreadsheets, but any of the service companies, they have a product champion that will sit down with you and input your formation and expected fluid properties, and you can get an idea of what the T1, T2 and diffusion should look like, and then that may help you help make sense of what the log is telling you. Okay, for a little bit about factor analysis to separate the different fluid signals. I've been reading some of those papers. Basically the way I'm seeing it is you have from job planning, you have an idea of what the T1, T2 and diffusion should be. And the other way, and they're not always what you expect. Sometimes you see things on the T1, T2 diffusion plots that don't quite make sense. They're not where they should be. So the other way of going about that is to just look at the data to see what T1, T2 falls out of the data diffusion, and try to figure out what it is. So, and in some of the papers I read, they were stacking the entire interval and see what the dominant T1, T2 and diffusion were over a given interval at a given fluid type, and then trying to come to an understanding of what those were, perhaps using other data to see what they actually were. And that helps, particularly helps in the case where the T1, T2 and diffusion are not quite what they expect. This especially came to be important in unconventionals, where very, very low, kind of low porosity, not much free fluid because they're shales typically, or low free fluid. And the T1, T2 and diffusion were not where they expected, or were not where they should be. And they're kind of a different understanding of what was happening in those situations because of the kerogen and bound hydrocarbon and so on. Kind of helped in those cases. And I can add that link to the Logic software. It's Logicom EP. Manganese, yeah, I'll have to look that up. Manganese, it's something, yeah, that could be it. But essentially it kills the NMR signal from manganese tetroxide.
Okay, Brian, we have one participant that would like to ask you directly a question. But Naslin, can you turn on your camera or your mic?
Okay, thank you. Brian, thanks for the presentation. It's very impressive. Just a quick question. Based on your experience, what is the maximum viscosity that you ever see in the NMR, even from logs or from the stationary cross plot?
The maximum viscosity. Let's see. Okay, let me bring up a slide and might be easier to show an illustration. Okay. It'll just take a moment for this to open. Let's see if I can find it quickly. Okay, I need to share this. Let's see here. Okay, so this is 3 different lab measurements. So 2.7 centipoise, the T2 is 609 milliseconds, 35 centipoise, 40 milliseconds, and then 4,300 centipoise, really pretty viscous oil, 1.8 milliseconds. So you remember that we said that the typical cutoff for bound fluid was like 33 milliseconds. Well, this all looks like bound fluid because the T2 is so low of the viscous oil. So it kind of tricks, it becomes in error to say that it's bound fluid. It's more of a viscosity indication. Also, if you get beyond this viscosity, the tools generally can't see a T2 below about 0.1, 0.3 milliseconds. So if you get over more viscous, you start losing signal at, you know, if it's very much more viscous, you just start missing porosity. So did that answer your question, or what? Theoretically, you can see some signal at a higher viscosity, tens of thousands of centipoise perhaps, but you start losing porosity. You just don't see it. Does that make sense? Or
yeah, actually, if you have from the real job, I mean, if you ever seen the max, based on your experience, what is the maximum viscosity you ever see in the NMR logs? Because this one of 4,000 centipoise, I mean, it's very viscous oil, and do you think we can see in the NMR logs for? I mean,
yes. In that viscosity, yes, thousands of centipoise, you can. It's sort of looks like all bound fluid, and at some point you start missing porosity. Mm-hmm. But that in itself can be an indication of viscous oil, how much porosity you're missing if you compare it to density porosity. Does that make sense?
Yeah.
Yeah.
That's cool. Thanks, Brian.
Okay. Yeah. Okay.
Okay, Brian. So we have two last questions. The first one is from Fiswanat. How to compare Stoneleigh permeability to CMR perms when the Stoneleigh perms are higher than CMR, or does the CMR perms higher than Stoneleigh?
Here's an example of that. If you can see the screen, this is from Baker. Let's see okay, the red is Stoneleigh permeability. The blue is from Emerald. So they're saying that in this case, that where the Stoneleigh is higher, that it may be fracture permeability. And this is in a more extreme case of that, the Stoneleigh is much, much higher than the NMR, and they're have an acoustic image and they're thinking that's fractured, tight fractured gas.
So usually when the Stoneleigh permeability is higher, then it is related to the fracture.
Yes, that's what this is indicating. High CMR perms are higher than Stoneleigh. I don't know about that. That means it, so that the CMR would be generally the matrix permeability. I'm wondering if one or the other is miscalibrated, perhaps. I can't think of a case of seeing that. And then the other question, how reliable is the irreducible
water saturation
from CMR?
Yeah.
In clastics, it's not. It's okay. Typically, the 33 milliseconds is reasonable cutoff in a lot of cases. We saw in some of the log examples we showed that where the peak moved, or maybe it should be 50 milliseconds, and it really varies by depth in the formation. There can be some variation. I would always benchmark it against core data. I think if the SWI is really important number for you, I tend to just look at the NMR and then try to corroborate it with some other data such as core data.
Okay, so it is very interesting night. So we have the last question from Pak Yulianto Jong. So someone told me that the formation water or drilling mud having high chlorine or boron content can affect the NMR signal. Is it right, according to your experience?
I don't remember about the boron. Here's the paper I was thinking about, formate brine drilling fluids in this paper from 2011.
Mm-hmm.
Oh, that was affecting the hydrogen index correction, not the T2 cutoff.
Not
okay.
T2.
But the boron, I don't recall that. It might, yeah. High chlorine. Okay. One issue as far as the sodium chloride mud was with the old emerald tools that are centered, transmitting across the borehole fluid, and that would tend to dissipate the RF energy. That was a problem. And you'd also get sodium resonance actually at certain borehole sizes. That was a problem. That's basically why all the service companies have gone to an X-centered tool to get away from those issues. Sodium, yeah, you can actually get resonance from the sodium. The chlorine, I don't know about the absorbing about that you could. I just don't know about that. Sorry.
All right. Okay. It has been a very enjoyable night discussing about NMR. Thank you. And that's the end of the Q&A session. So I will pass it back to Mbak Dian. Please go ahead. Thank you, Brian.
Thank you. I'll pull up the link for the Logicom and put that there on the screen or on the chat box.
Okay. All right.
All right, thank you very much, Brian. So as a token of appreciation, we would like to present you the certificate from SPE Java Indonesia. Unfortunately, we cannot provide this or deliver this directly to you because of the current condition, but I hope this can show our big appreciation for your time and effort on sharing your valuable knowledge with all of us. Yeah. A big round of applause for Brian, please.
Thank you very much. Thank you for that. I would rather come and pick it up in person.
Yeah.
I always enjoyed being in Indonesia. Maybe sometime.
All right. So thank you very much again, Brian. And that's the end of our technical discussion group session. On behalf of SPE Java Indonesia section and SPWLA Indonesia chapter, we would like to thank you all for attending. We have a very great participant today, more than 100 participants. So that's a very good turnout. Yeah. So for the participants who wish to get some e-certificates from SPE, please, we will provide you after you provide us with the feedback in the link on the screen. You can also access the link in the chat box. So before we end, let's take some picture together to document this session. Everyone, please turn on your camera and then we'll take a picture together. Mbak Fanya, please, can you help us take the picture?
Okay, Budian, maybe you can stop sharing your screen.
All right.
Everyone, please turn on your camera. Okay, I will take a picture for the first page. Okay,
Let's wait for another minute, Mbak Fanya, maybe, yeah. Maybe some people still want to be representable before, before taking picture. Okay, everyone, please turn on your camera once you are ready. Okay, Mbak Fanya, let's start the session, the photo session.
Okay, okay, ready ya? In 3, 2, 1, smile. Okay, second. Wait, second page. In 3, 2, 1. Okay, last one. 3, 2, 1. Wait. Okay.
Okay, done?
Yes. Thank you.
Okay, thank you very much. So again, please do not forget to give us your feedback. We'd like to hear from you. This is the end. Please stay tuned to our social media for upcoming events. Thank you for all your attendance. Good evening. Stay safe and keep healthy.
Thank you.
Stay safe, everyone. Thank you.